Geometry. What is geometry, and how exactly do we constitute the way geometry is defined? In this video series, I'll be focusing on axiomatic geometry, like how we have proved certain triangle congruencies, or learned about special shapes, like the Sacchetti quadrilateral. In this video, I'll be going over the history of geometry and how Euclid transformed the way that we think of geometry today. Geometry is derived from the ancient Greek word geometria. Geo meaning earth or land, metria meaning measurement. However, geometry as a whole covers much more than just measurement, expanding to things like explaining the relationships between shapes or the nature of mathematics and numbers. Before we take a look at any of the foundations, we have to understand the history of how geometry was first used. The earliest recorded beginnings of geometry can be traced to the early peoples of ancient Indus Valley and ancient Babylonia from around 3000 BC. There was a collection of discovered principles around lengths, angles, areas, and volume. They used geometry for its practical use in activities like surveying, construction, and astronomy. And around the same time period, ancient Egypt used geometry mainly to survey and to preserve the layout of their farmland from the annual floods, but like many ancient civilizations, geometry was seen as a tool to aid them with more practical matters. Then we get to ancient Greeks who had theoretical discipline and used deductive reasoning and proofs. The Greeks pursued with intellectual endeavor, which makes them very distinct compared to the preceding civilizations. There are many important figures of ancient Greek geometry, but we start off with Thales of Miletus. He is thought to be one of the 7 wise men of Greece, and even though there is very little documentation of his life, he is considered to be the first to attribute logical deduction in mathematics. Moving on to Pythagoras of Samos, he has made many mathematical discoveries, like the Pythagorean theorem, which many people are probably familiar with, but the existence of Pythagoras himself is actually not confirmed. A brotherhood called Pythagoreanism was formed, which focused on using math for ideological and mystical reasons without any practical applications. Then we have Plato of Athens, who is not specifically a mathematician, but he contributed ideas that greatly influenced the way math was approached. One contributing idea was that the use of a straight edge and compass are the only things needed to do any proof or construction. This will be the foundation of how we will do many of our following proofs. Finally, we have Euclid of Alexandria. Euclid is often referred to as the father of geometry because of how he introduced mathematical rigor and he used the axiomatic method. One of his books, Elements, is widely considered to be the most influential textbooks of all time. But why exactly was this book so impressive? Elements was so impressive because of his axiomatic approach, constructive methods, and the level of rigor used to discover theorems. Elements is actually segmented into 13 smaller books that cover a variety of topics like conics and number theory. Not all of the content is original information and refers to the findings from previous mathematicians, but it is a bit hard to distinguish the original finders since ancient works were not that well documented. However, it is still an impressive accomplishment of assembling and filling in the gaps of mathematical knowledge that continues to be referred to well past the 19th century. One question you may be wondering is, what is an axiomatic approach and how is it used? The axiomatic approach is a method where mathematics is developed from a few axioms and definitions from which we logically find new propositions or theorems. Some terms that we should be thinking about are axioms, definitions, and propositions. Primitives or definitions are the most basic ideas that include objects or relationships. The terms themselves are undefined and could be anything with no intrinsic properties. Axioms or postulates are statements about primitives which we assume to be true. These cannot be proven and are the building blocks of geometric concepts. We need some assumptions because not everything can be proven without a solid foundation. And lastly, propositions or theorems are statements derived from axioms using deductive logic. A helpful analogy to understand the relationship between the terms is a comparison to language. We can think of it as like primitives are like letters, axioms are like words, theorems are like sentences, and logic is like grammar. Looking at letters or primitives, these have no intrinsic meaning, and they can be any symbol we desire. They're just the foundation that tells us what we can use to create words. Words or axioms, these have no meaning by itself, and is just a group of letters and symbols. However, depending on the order and combination of these letters or symbols, we can give them meaning. The meaning of the words cannot be proved, and we just assume that as a given. We can use these words to form sentences, but without proper grammar, the sentences will just look jumbled or meaningless. We have to use the proper grammar and use the appropriate words to communicate meaningfully. Now, let's see how each of these components are implemented in Euclid's Elements. In the book, there are 23 definitions, but here are some examples of what they look like. Although some of these definitions may seem very intuitive, it is their purpose to define basic objects. For example, definition 1 and 2 tells us what a point and a line are. Now it is important to realize that some of these ideas can also seem very vague. Many of these definitions are not very rigorous and is only understood within the context of the book. For example, the first definition says a point that of which there is no part. However, there is nothing in our physical world that has those properties exactly, making the meaning inferred. There is also a lack of completeness and gaps in definitions that led to the realization that there are two kinds of technical terms or relations. The meanings are pretty self explanatory, with terms being a defined object and relations being the relationship between terms. An example of this can be seen with definition 4. A straight line is a line which lies evenly with the points on itself. This definition relies on the terms point and a line to apply it to the meaning of a straight line. Alongside these definitions, Euclid added 5 common notions, which are basically normal axioms but are applicable to everything and not just geometry. One important assumption that isn't explicitly stated is the notion of intersection and the guaranteed existence of a point at that intersection. I won't go into too much depth into the meaning of each of these notions or postulates, and we'll be covering over the more important ones in later relevant videos. Moving on to the postulates, these 5 postulates are what first defined what we call Euclidean geometry. At first glance, this last postulate may stand out for how long and complex it is in comparison to the other 4 postulates. However, there is a very big significance to this postulate, but we will also cover this in a later video, why it is so necessary to make the geometry work. However, most of these postulates are very basic and mainly tell us what we can do to construct objects. Let's briefly look at the first proposition to see what it would look like. Our first proposition given by Euclid is to construct an equilateral triangle given a finite line. When we're trying to prove this theorem, the only thing that we can use are the given postulates, definitions, and other theorems if we prove them beforehand. Since it says that we're given a finite line, let's just start off with 2 points, A and B, and using postulate 1, we can make a finite line from point A to point B. Using postulate 3, we can draw a circle and have its center be around point A, and the radius is the distance from point A to point B. We can also do the same thing, but this time with the center around point B. We can see that these 2 circles intersect each other at 2 different areas. But let's only focus on the top one, and let's call that point C. Now, let's draw a line from point A to point C, and point B to point C. Well, we know that the distance from point A to B is the same distance from point A to C, because both of these lines are the radius of the circle. We also know that this applies with point B to point A and point B to point C. We know that all 3 lengths of this triangle are the same, so this gives us an equilateral triangle, thus proving our proposition. This is a very basic proof, but it allows us to see the interactions between definitions and axioms to discover new information. Even though Euclid's discoveries and approach to geometry were groundbreaking, there were some flaws in the clarity of the structure. That's where Moritz Pasch came in. Pasch was the first to rigorously attempt to axiomatize the Euclidean plane and to draw attention to the number of assumptions made in elements. He was not falsifying the information, rather he argued the mathematical reasoning should not invoke interpretation of the primitive terms, and should solely rely on the formal manipulations justified by axioms. One of his notable contributions of axiomatizing Euclid was through his axiom of separation. It'll be shown later on what this axiom looks like. Later on, David Hilbert focused on developing a postulate set for Euclidean geometry that did not derail from Euclid's ideas, but had more rigorous axiomatization. He does so by stating or proving explicitly the assumptions Euclid had made, basically filling in any gaps or polishing any information. Starting off with the primitive notions, Hilbert categorizes these into terms or relations. The three terms are point, line, and plane, and the three relations are betweenness, incidence, and congruence. When we talk about betweenness, we use the asterisk notation and is denoted by A, B, C, which would explicitly mean that B is between A and C. After the primitive notations, Hilbert creates 5 different sections with axioms that relate to the corresponding categories: incidence, order, congruence, parallel, and continuity. When looking at the different axioms, it is a good exercise to try and make a visual for each of the following axioms to get a better understanding of how to use it or what it would look like. For the axioms of incidence, they look very standard and shows how we are able to construct certain objects and the properties they have. For example, we can see this in axioms 1 and 2. Axiom 1 allows us to construct the line that gets us from point A to point B, but then axiom 2 tells us that there can only exist one line that lies on point A and B. You may notice that we can have more than one curve that goes through point A and point B, but this wouldn't actually be considered to be a line. That would be a curve. For axioms of order, they tell us how we define betweenness and what do we mean by intersection. As brought up earlier, we can see Pasha's axiom being implemented here. This axiom is easily visualized with a triangle and basically states that if a line enters through one side of the triangle, it must exit through one of the other two sides, assuming that we are not allowed to go through the vertices. The axioms of congruence is pretty self-explanatory, explaining how we defined what is congruent. Looking down the list, axiom 5 may look very familiar. This is because this is actually the SAS triangle congruency, if you remember from middle school. It may feel very strange how this congruency is part of the axioms, but it is actually an essential axiom for geometry. Going on to the axioms of parallels, even though there is only one, it is also very significant, and we will be covering that in a later video. Moving on to the final axioms of continuity, these axioms are not too important, but actually complete the space. The main thing to look at is the second axiom that states how it would be impossible to add to any of the other previous axioms without creating this new type of geometry. Now obviously this is not needed for the development of Euclidean geometry, but is rather used to establish a bijection between real numbers. And with that, I just hope to show the evolution of how we discovered and defined how we think of geometry today. I hope to continue this series, and in the next video, I'll be focusing on how to construct these different types of geometries and what it would look like if we change the axioms or definitions we used. I'll see you next time. Thank you for watching.